Okay, so if you look at the columns here, you will find that there is a little change in the way the loading takes place. Okay, so suppose you look at this column, it would be an I section. Then on a bracket, you have another section running. Okay, this is again another I section, and on this the crane girder will run up and down. Okay, so now if you look at it, the load is actually, this is the column, load is applied at this point. The load P is applied with an eccentricity E. So what happens here, a moment M, which is equal to P into E, gets generated. Okay, so now this is the principal condition with which most of the columns get designed. That is, columns are designed for axial force and a moment, for an axial force and moment. Okay, now here there is a problem. The column which is here, because I'm applying a moment, it would take a bent shape like this probably. Okay, now had I got another moment on the other side, okay, if I'm having a moment on the other side also, what would happen is both of them will cancel out each other, so there is no net moment. Okay, there's no net moment. So this is the thing which we are just trying to show here. So if you take a typical building frame, you will have a combination of an interior column. Okay, so here this is an interior column which is predominantly axially loaded. If you have a column like somewhere in the middle of the building, so you got a cross beam which runs across the length like this one, and two beams which are having equal moments. Okay, the dead load moments on both of them are equal. They'll cancel out each other. So it means that predominantly this column has bending in only one axis. Okay, the moment is only there in one axis. On the other hand, a column at the corner is going to have moment in both the axes. The column is going to have moment in both the axes. A little later on, this principle would you will have to recollect. I would appreciate, you will just need to recollect, and this is a very important point which you need to remember. There is no column which comes as purely carrying only compression. Okay, there's very rarely, it's very rare that a column is going to carry only compression. Okay, so we'll go on to find what are the types of compression members. So these are the typical ways by which you get compression members. Now I told that you can have columns which are even up to 3 meter in depth. So all those are typically done with these welded sections. Okay, these are built up with individual plates. So they'll be built up and connected together by welding, and some other stiffeners will also, so weld will be provided here, but in addition to that some stiffeners will also come into the selection. Then for minor loads you can even use simple angle and channel. For example, if you're going to have it in a truss, you may be able to design it with a angle or a channel. It doesn't mean that you have to only go for the I sections. Okay, you don't have to go only for the I sections. So you can go for angles and channels when the load which is going to be applied is very less. So then we've got the built-up sections. What are built-up sections? They are sections which are made up from smaller elements. Okay, for example, you got the laced columns. Okay, do you remember this section in particular, please? Where have you seen this section? Have you seen this section? Sorry? Foodies. Okay. Any other guess? I don't know. I think I don't have foodie section in particular. Yes. If you go by train, the support for that electric traction is by this section. In particular, this is a laced column. Okay, this is what we call as laced column. See, there are two channels okay, which are which are attached together. This is channel number 1, channel number 2, which are connected by flats. Okay, flats is nothing but a flat section, okay, or plates. Okay, so this is called as a laced section. Okay, battened columns are ones which typically have okay, I don't have Batten. I don't have a photograph immediately of Batten section. So instead of the lacing, you will have plates connecting the two columns. So this is called as the um, Batten section. Cruciform section will have a I pattern like this. Then you got built up plated columns. Of course, built up angles and channels is what you see in foodies. Okay, in foodies, you got four angles which are connected together to make up a column. Okay, so these are some of the examples of built-up sections. What is the benefit of built-up section? The individual I section, what you will require for a moment and for an axial force. To achieve an axial force and a moment will not be possible to be got economically. It means you'll have to use a very huge I section. To use a very huge I section, what is the problem? One, cost is very high. Second, wastage is very large. Okay, so if suppose I'm wasting 1 meter of a 200 kg per meter column, just like the 200 kg becomes scrap. On the other hand, the same effect could be got by say 5 or 6, I mean 4 sections with 20 kg per meter run. So 80 kgs might have been the wastage, is the wastage which you get when you use individual elements. Connecting a very big section is very difficult. Okay, to weld thicker sections, you have to use very specialized techniques, because when you weld, the thick section can absorb heat much more. Okay, so by the time you get an appropriate temperature for welding, the section might have cooled off. Which is a problem. Again, you have what is known as HAZ, heat affected zone. Okay, so when you are having thicker sections, all these sort of problems come into the picture. Okay, so it's always better to go for smaller sections. And in fact, this cruciform section what we are talking about is very good, because the desirable I value of Z is there in both the axes for this column. But then, do you know how they manufacture the cruciform section? It's not a rolled section. You'll take an I beam, okay, you take an I beam, cut it into two, okay, then you take another I beam, weld this together. So what happens is, when you are making a built-up section, you may wind up with using a lot of weld. Weld is very costly. The weight of the weld is also increased, and then when you cut, you need to cut very carefully. If you are not cutting in a very nice and straight manner, these two parts which you cut will be scrapped entirely. Okay, so it's very difficult to make cruciform section, but then we used to design that when we used to design such sections when we felt that we didn't have option. So usually what happens is, in a design office, you will have a set of sections only which are procured. So it means that ISMB 200, next maybe only 350. So between that there will be no section available. So it means you cannot use other things. So that would be one reason why you go for some crazy things like this cruciform section. Of course, then there are these closed sections, pipe sections, and rectangular hollow section or circular hollow section, square hollow section. All of these are there. As an example, where have you seen pipe sections as columns? Have you seen pipe columns section as columns? Yes, where? Walkway. Can you think of the walkways in VAT? What is the section we use for columns? Right. Then there are these purlins to support the roof. What are the sections which are there? Choose the best. Angles, channels, rectangle hollow section, square hollow section. Rectangular hollow sections are there. Okay, so all these sections are available in our campus. Just have a look at how they have detailed it. Okay. Now I'm going to go to something which is a little more involving. We are going to study what are the factors that constitute an ideal column. We are going to just see what makes an ideal column. Now this probably you would have studied in your strength of materials. Okay, column buckling is a topic typically handled in strength of materials. So first thing we say, it's a perfectly elastic material. Elastic material stresses are proportional to strains throughout. Wherever you are loading, whatever be the loading value, strain will be proportional. Then you load through frictionless spin. In other words, you load at the CG of the column. The loading is done through the CG. So this is what we say when you load it through frictionless spins. Then we also say that the column is initially perfectly straight. What happens if a column is slightly bent? I don't know if you have noticed this. In your cycle, if one of the spoke is slightly bent, what is likely going to happen? If a spoke in the bicycle or motorcycle is bent, what would happen? It is more likely to buckle and fail. When one spoke fails, all the other spokes are also likely to fail. So this is what happens when you are not having a straight column. Again, you will also have something where it says it does not fail locally. An ideal column is expected not to fail locally. For example, look at this column. It has failed only in this region, locally in this region. Okay, so you don't expect a column to fail in any one of the portions locally. Okay, but in real life it doesn't happen. There is no such thing as a perfectly initially straight. So all this is ideal condition. So if you look at the reality, none of this is possible. Okay, now we are just coming to this equation. Okay, this is called the Euler's equation, and it gives the crippling load or the failure load of a column. Okay, PCR typically stands for crushing load of column. Okay, now this is nothing but in your moment distribution method you have used this equation. So when you just frame the equation for this column, this y is the eccentricity or the amount it bends. Okay, you will find that the solution for this is this one. And again, if you look at the textbook, or this is from the INSDAC manual, the various solutions which are possible for that differential equation are pi square ei by lambda square, 4 pi square ei by lambda square, so on and so forth. So what happens is, first the column is initially straight. Okay, that is our assumption for Eulerian column. Then it will start to bend. It will take one bent shape. Then when it goes for the second mode, okay, this is the first mode, this is the second mode of failure, it will take two bend. Okay, then when it goes for the other one, it goes for a third bend, so on and so forth. Okay, but then the moment this condition is arrived, the column has already failed. So these subsequent cases happening is not practically possible. Okay, so what is this buckling? Buckling is deformation of the column in the lateral direction. Okay, deformation of column in the lateral direction. Just remember that book which we saw bending. So the column deforms in the lateral direction. The column deforms in the lateral direction. Y. Okay. Now I'll need to zoom out a little. So this is the reality about columns. there is a non-linearity in the stress strain. Why is this non-linearity appearing? You don't expect non-linearity in a steel material, because when you are producing the steel, stresses can get locked in. Okay, some stresses get locked in. So this causes a non-linear behavior of the stress strain diagram. Again, there are so many accidental imperfections. If you see how many times is a column lifted very carefully and kept, you'll find that they just dump it, they just carry to the crane, drop it. So all this could cause imperfection. Again, loading is never through the CG. Loading is never through the CG. For example, we saw the crane girder. What is the chance that you are going to have concentric loading? It's not possible. Again, the shape of the cross section itself might be unsymmetrical. Okay. For example, you take this angle section. When you take this angle section, which is the axis of equal bending. So if you look at the centroidal axis, it is here. Yeah, you got some other angle. Okay, if you look at your section, you will find that there is a UU axis and a VV axis. I think I'm mixing up the UU and VV. Please have a look at the IS800. You will be given two more axes. Okay, so it means that the cross section plays a very important role. Cross section, that would be in the orientation. Okay, the orientation of cross section, somewhere in the beginning it is given. Again, there is a torsion which occurs. The torsion is the twist, okay, which will come as we go on. Okay, because a section, when it's compressed, it need not only bend, it can also twist and fail. Okay. Again, shearing, deformation, local buckling, like the photograph which I showed you. Again, method of fabrication also plays a very important role. If you look at a very thick section, what happens after you weld is you need to do a annealing process. Okay, but how many sites will be able to do the annealing process? Literally none. Okay, this causes a lot of what we call as the residual locked-in stresses. Again, there's a continuity action of frames. It means although this is a column, okay, now when I'm having a element framing into this, some tension comes probably from the bending moment and sometimes a compression. So typically what happens is something like this is going to happen. The frame causes a tension compression action to take place locally here. Okay, a tension compression system locally forms at the place where the joint is there. So this causes the stiffness to change. This causes a change in stiffness. Okay, so when bending moment is there, tension will increase the stiffness and compression will reduce the stiffness. Okay. Last thing which we have here is the residual locked stresses. Now have a look at this. This is again taken from the Instack book. Initially, a rod is subjected to some rollers. Okay, so there is a roller with very heavy force applied. Sometimes when it's a hot roll section, the entire bar is red hot. It's molten, so it makes it a little easy to roll it. So first it takes this shape, second, third, so on and so forth. So the thick bar has now become a very thin section. Now what happens is when you roll, the flanges which are outside, they tend to cool off much quicker, okay, when compared to the center. Now this causes a differential strain that results in a bending pattern like this. Okay, so this when you are superimposing the live loads or the loads which come on the column, it gets a load pattern like this. Okay, which is not linear. Which is not linear the way you expect it to be. Okay, so this is the thing or these are the factors which affect the strength of the column. Okay, now would you like me to explain any one of, I mean, like, do you have doubts in any of these points which we spoke about? Or is it all Greek and Latin here? So, any doubt in what we have seen here? Yes, what is it? Right, sorry? Okay, so fine. So you'll find that all your formulas are based on the ideal column, but then the ideal column never happens. The ideal column never happens. So we are forced to take into account all of these imperfections, and that is why the code may not have values which you expect, like which you calculate and have to be there in the formula outright. Okay. So again, we are just going in to look at the buckling of column, which is a very important mode of failure of a column. Buckling failure is an important mode of failure of a column. So buckling increases. So if you look at this formula, buckling increases when L is more. Again, when E or I is there, the effect of buckling is reduced. In other words, what do I mean by this? If I am increasing L at a very low value itself, P critical will occur. So buckling increases. Critical load of the column is much lesser when your length is increased. Then if I am increasing the stiffness of the column, what happens? Automatically the crippling load reduces. Okay, the crippling load reduces. Yeah, what is that you are having here? Okay. So now look here. This is what we mean by putting these arrows. When I am increasing the length, you are going to find that at a very small load, your column is going to fail. Okay, just think of a bamboo pole which you are able to make it have an unsupported length. Okay, so you are having an unsupported length. So initially you are having a very short strip, only about half meter. Is that guy disturbing you? The one next to you, the orange shirt. Is he disturbing you? No. You are disturbing him. Okay. So look here. So when I am keeping on increasing the unsupported length, what happens is even at a very small load, my column is going to fail. Okay. So this is the principle of the design of a column. So if you are going to have a long unsupported length, you cannot avoid it. What is the thing which you try to do? You try to increase I. Okay, PCR is the ultimate load which the column can take. Okay, PCR is the crippling load which the column can take. If I am going to increase, PCR may be a constant, but then the height at which it happens might increase. Okay, so when the height increase, the only parameter which I can play around is I, because E for a steel is constant. 2 into 10 power 5, you cannot change that. Okay, so all the E and I you can modify. The only parameter which is in the control of a designer is I. Got it? Okay. So it also means, for example, I am keeping two I sections at a distance of say 500 mm. Okay, and then I am keeping two I sections at a distance of 1000 mm. Okay, so now if this is x axis and y axis, along which axis will I change? Will Ixx be large or Iyy be large? See, between these two, there's an increase, okay, of moment of inertia. which moment of inertia increases, Ixx or Iyy? See, Iyy, you're right, because the distance from axis y is increased. The distance from axis y has increased. So that is why Iyy increases. This is the way by which a designer can increase his y value. Okay, because we'll come back to this. I'll come back to this principle a little later, but this is a learning which is very important. Okay. Now, these are the failure modes of a column. There are basically two failure modes. One, due to crushing or due to compression, it fails because the force is so high that steel yields, or it just is not able to take that load. Okay, so that is crushing failure. It happens when the size of the column is very short. Okay, so if suppose Fy is being taken by this, I'm sorry, if P is taken by this column, let us say that both this column 1 and column 2 have the same area of cross section. Sorry, column 1 and column 2 both are the same cross section. However, what would happen is, when I am going to take this column, this will yield at a load which is less than P1, maybe much lesser than P1. That is because of the buckling which comes into the picture. All the area is same. The problem is the I value is the same, but the length, the unsupported length is different. So the column could fail in buckling. Okay. And again, there's another example. So if suppose you see this is a bar, both the bar and the tube have the same area of cross section. So for example, if suppose this is D1 and outer diameter here is D2 and inner diameter is D3. Okay, so A1 is equal to A2. But then what is changing here? What is the value which has changed here? The value of I has changed. The value of I has changed. It means that the second section is more likely, will take a much higher load when the unsupported length is larger. Okay, so if you look at the amount of steel used, which is using more steel between A1 and 2, which column section carries more steel, which is using more steel? Both are same, because area of cross section is same, length is same, so the amount of steel used is same. Okay, now I have a question for you guys. Now look at this. In fact, I wanted to put this on Moodle. I wanted to have a series of questions in Moodle, but today I didn't get as many questions to warrant putting it in Moodle. Now look here. Let's see, roll number 44. We need 44 here. Okay, let's not disturb the persons who are sleeping. Okay, the one in the yellow shirt. Which is the stronger axis? Yeah, please. One in the yellow shirt. I've got two axes here, Ixx, Iyy. Which is the stronger axis? You have to give your reasons. Sorry? No. In figure 1, there are two axes, Ixx, Iyy. Iyy. Why? Okay. If you are you having a if you are having 808 or SP61, you will find that suppose I am taking ISMB 450. Typically, this depth will be much larger than this width. Okay. Again, this causes material to be dispersed much beyond the CG of the system. That makes Ixx the stronger axis. Okay. Now, would you like to try again for the your favorite section number 3, which is a stronger axis? Huh? Let us say that this is IS angle 6066. Which is the stronger axis? Ixx or Iyy? Any other okay, any other person? Yes. Which is a stronger axis here? Huh? Third. Very good. Both are having the same properties. No clapping. Look here, guys. So if you are looking at it, both the lengths are same. It is symmetric about both this axis. So it makes it strong about both. Then what about number 2? Yeah, which is the stronger for figure 2? Ix or Iy? So here what happens is, here X is again going to be the stronger axis, Y will definitely be much lesser. So what you do is, you will take 2 of these angles. This is what you saw in that photograph. Then you see how much of I you require. So to that level, you increase the distance. Okay, you will increase the distance. Now your column has sufficient Ixx and Iyy. Your column will have sufficient Ixx and sufficient Iyy. So the principle you need to learn here is, to design a column, you have only one thing to play around with. For taking the compression, you need to provide minimum area. Area you cannot compromise. But the other parameter, to control buckling, you can or you should play only with your I. You should only play with your I value. Okay. So you keep moving it, but please remember there is a limit to which you can keep moving sections. To connect the two, to design this lacing itself will then become a problem, because this lacing transfers force by compression tension mechanism. It's a truss. Okay, so this the lacing element would become so long that it would become impractical. Okay, so how do you actually go about effecting a saving? You see various section. Will it be possible for an IS MB to take the load by itself? If it is a no, it might be because the column is weaker about one axis. This is where the principle of the location of the column comes into picture. And column which is in the middle of the building may not have any moments at all. If you just design for axial loads, it is more than enough. But a corner column, it is having a moment in both the directions. It's having a moment in both the directions. So you will have to start to think whether this is going to work or moment about this is going to work. How am I going to play around with values of I? Okay, the last thing I'd like to say is, there's a concept of effective length. What is this effective length? It is, in my language, the distance between 2 points of contraflexion in a column. Okay, so the place where the bending moment is going to change sign is going to determine the compression or tension, the compression length. Okay, so if you look at it, the effective length, that is the length of column may be any length, but then buckling is only going to take place between this region. Buckling is only going to take place between this region. So this region, it will not buckle at all, because the effective length, the length is so short, so it's not going to fail there. So only between this length it is going to fail. So this is why you got this effective length parameter. See, if you see here, it is only 0.65 for fixed on both sides, but for a cantilever it is actually 2. For a cantilever, effective length is 2. It means wherever L comes into an equation, you will replace it with 2L. On the other hand, for fixed on both sides, wherever L comes, you will replace it with 0.65. 0.65. Okay, so we've seen in today's class the failure modes of column. Okay, because this is going to determine all the formulas which we are going to study in the subsequent classes. Is it okay with all of you? Guys, is it okay with all of you?